All right, so this is looking at applications. This is section 3.3, looking at applications of exponential growth where we're given the rate of change, given the growth constant. So we're going to do a couple of examples of those cases. All right, so the first case is a population example. Suppose we know that the population in millions, I've got to remember when I go to put my units that it's in millions, of a certain city 2 years after 1990. All right, so 1990 would be my time zero. All right, satisfies the differential equation, its rate of change, and that should be a t, not an x. All right, its rate of change function is equal to 0.02 times the population size, right? P of t represents the population size. And so what that equation is telling me is that it's exponential growth. It's growing by 2%, right? That's what this means. It means our population P of t is growing by 2% per year. All right, the initial amount was 3 million, all right, at time zero, so when the study was started, 2 years after 1990, so 1990 would be my initial time, and so we started with 3 million people, and so that would be my initial amount. All right, so the first question is then, what was the population in 1998? So 1998 would be looking for time 8, right, 8 years after 1990. All right, before I get started, though, I have to set up my equation. All right, so my population satisfies, right? It's growing at a rate proportional to its size. It starts with 3 million. I'm going to write 3, just remember everything's in millions. E raised to the k, well, the k is the 0.02 times time, all right, in millions of people. All right, so there is my population equation. That's the differential equation that satisfies this information. Right, it's growing by 2% per year, and we started with 3 million people. And I do have to remember my units are in millions of people. All right, so the first question is just asking you to find the population after 8 years. All right, so population in 1998. So again, just take my 8 and plug it into this equation. And I'm just going to round a couple decimal places. All right, so if you plug 8 in, it comes out 3.52. Remember, always put units. And so in 1998, the population was 3.52 million people. Right? Those would be the units, million people. All right, so 3.52. So it grew by about a little over 500,000, right? In 1990, we were at 3 million. In 1998, we were at 3.5. So it grew by about 500,000 people, and it's not growing real fast, right? 2% is not an incredibly fast rate of growth. It's a fairly small rate of growth, so it should make sense. It's not going to grow leaps and bounds in 8 years, but it is going to grow by about 500,000 people. All right, the next question. When will, so in what year, we're looking for time, the population reach 4 million? And so this time, we're given a quantity, and we want to solve for time, right? Our time is what? Given, after that time period, we reached 4 million. And so I'm going to take my equation, right, this equation I found here, and set it equal to my 4 million and solve for the time. A similar process to what I talked about on the last set of notes. All right, so 4 equals my equation, 3e to our k, 02 times time. First thing, divide by the initial amount, 3. And so I have the fraction 4/3, right? That would be the quantity that we're looking for, 4 million divided by our initial, equals e raised to the k times time, right? Times what I'm going to solve for. Find the natural log, and so we get the natural log of 4/3 equals 0.02 times time, divide by our 0.02. All right, and so there's that formula, which I said if you wanted to memorize it, you could. All right, it's the natural log of the quantity we were wanting to find, quantity at times t, divided by my initial quantity, 3, all over my growth constant. Now, it's up to you. You can either memorize this equation, it's fine, and if you do, when you're solving stuff, show me this step. Or if you want to set it up and solve it this way, you can solve it that way. Either way is fine. It's up to you if you want to set it equal to and go straight here. All right, and then make sure you're careful when you're plugging it into the calculator. Remember, it's the natural log of the fraction 4/3. All right, so the 4/3 is in my natural log. And then you divide by the 0.02. All right, so I'm going to round my time a couple decimal places. So it comes out 14.38. So remember, that's years after 1990 when we started. So in what year? All right, so you'd add 14 to 1990. So it would be in the year 2004. All right, 0.38 into that year, but in the good enough answers in the year 2004. All right, the next part. In what period of time did the population double? So how long will it take my population to go from 3 million to 6 million, right? Double. And so again, it's a lot like the previous answer. I'm looking for time, right? I'm actually specifically looking for doubling time, right? This is my double time. And there's two ways you can do it. You can either remember that doubling time is the natural log of 2 divided by my growth constant. So natural log of 2 over the 0.02. And that's fine. If you remember that little formula, you can just use that. And so if you take the natural log of 2 divided by a 0.02, it comes out 34.66 years. All right, that's how long, that's my doubling time. That's how long it takes it to grow, to double. All right, so in 34.6 years, it'll grow from 3 million to 6 million. In 34.6 more years, it'll go from 6 million to 12 million if it stays consistent at growing by 2% per year. If you forget this, you could always do similar step to what we did here. I know that we're looking for the doubling time, which means I want to find when it grows to 6 million, right? Twice what I started with. And so you could take your 6, set it equal to your equation 3e raised to the k times my doubling time, and then solve, right? And so you'll get, all right, k is 0.02, I didn't put it there, the same expression, right? When I go to solve this, you're going to end up with the natural log of 2 divided by our 0.02. All right, and so you get the same answer either way. So it's up to you. You can memorize this equation, or you could solve it like we did in the previous example. So you pick and you choose which way you want to do it. All right, the second one. All right, so this is where we'll stop today's notes. This is going to be a short one. All right, this is actually a book problem. All right, so this is from your book. All right, so we have Pete selling franchise pizza shops throughout the country. His marketing manager estimates that the number of franchises N, so N represents the number of franchises, will increase at a rate of 10% per year, which is actually fairly big. So again, it satisfies this differential. All right, it's growing by 10% of its size. All right, how many franchises you currently have. All right, find the function that satisfies the equation. Assume the number of franchises at the start times 0 is 50. All right, so that's my initial amount. All right, so for A, we're looking for an exponential growth equation. So n of t and not e raised to the k times time, and they gave us those. All right, we started out with 50 franchises, so that's my n of t. They told us our k. All right, k was 10%, which is 0.1 as a decimal. And so my equation is my franchises equal 50 e raised to the 0.1 times time. Right, and so there's my equation that will assume the number of franchises, that will find the number of franchises t years later. All right, then we'll use it. Part B. How many franchises do they expect to have in 20 years? So time is 20, so let's just plug 20 into that equation. And since we're talking about restaurants, right, that's what franchises are, like restaurants, don't give the decimal, right? You can only have a whole franchise. And so this comes out 369.452, so I'm going to round to 369 franchises. Pizza franchises, if you want to get more exact. Alright, and so there's the answer to B. Alright, so C is asking for when will they double? So we started with 50. When we know how long it'll take to grow to 100. So again, there are two ways to do this. You can either remember that the doubling time is the natural log of 2 divided by our growth constant. So in this case, it'd be the natural log of 2 over 0.1, and that comes out to 6.93, or I'd probably just round 6.93 to 7 years. So in 7 years, it should double. All right, that's the doubling time. So in 7 years, they should have 100 franchises. In another 7 years, they'd have 200 if it continues. And another 7 years, they'd have 400. All right, so that's what the exponential growth is. If you don't remember this equation, you again could solve it similar to what I did up here. All right, you would set your equation equal to the double and solve it that way. All right, so again, it's just up to you. All right, so we're going to stop there. The next examples, we are going to do applications of exponential growth in the next one, but the next examples, we're not given k, we have to find k. So we're not given the percent at which it's growing. We're not given this information. We'll have to find that. All right, so we'll pick that up in the next set of notes. So we're going to stop there.